Hey there, year 12s. We're going to look at this example here. Now, in order to do this example, I would encourage that you watch this video that I put in about ESTs, LST, and critical pathways. They talk about forward scanning and backward scanning to help you understand the general gist of foundation before we get into doing this activity. But feel free, you can watch me as I do this, and then that way you get a better understanding of how to get going. But let's go. It says the project has 6 activities. You got A, B, C, D, E, F. That's your 6 activities. And we're going to convert this precedence table into an activity network, which is what we're going to do part A. So we can see that A and B do not have any predecessors. So we can start off with A and B. So here we go, A, B, and we know the weights are 6 and 9. And then we can see that C is connected to A and B. So C cannot start until A and B are complete. So we can see that if I drew out C, this is the activity for C. C cannot start until B has complete. And I'm adding in a dummy because that's the only way where both points will then come towards C. And once they do this, I'm going to do a little d with a capital B to indicate that that's the dummy coming from B, and I'm going to give it a weight of 0. So now we can see that C comes after A and B have completed their task. And then after C, we can see that D is the same thing. So that means D can probably come out, and I'll just do D over here. Again, D comes off the fact that it has A and B in the same manner, but it has no relationship to C. So it's another separate branch there. But keep in mind, if we're looking at the end, and I usually like to see the finish line, so F has a connection to C and E. So C's here, and I can connect F just like that, right? But there's a problem because there's meant to be another E component, but E also has a predecessor of D. So I can see that what I might do then is I might connect an edge, and I'd say that this is E, so that E connects back to F, and both C and E, once they complete, that's when F can start. So if I put in the weight, C is a weight of 8, whilst E is a weight of 10, and D is a weight of 7, and F is a weight of 12. There we go. So that now makes sense with the network. I've got my precedence table transferred into an activity network. Now B, let's have a look at what B is asking us to do. So B says, complete the critical path analysis to calculate the EST and LST. Now, if you watch the video, I feel like the critical path is like doing a Dijkstra's algorithm, but looking for the longest pathway. Because you want to know what is the minimum amount of time needed in order for the activities to be done. So for example, C, right? C cannot be done or cannot start until A and B is done. What we can see here is you can start off a time. I'm just going to put in the boxes starting from here. You see the time starts off at 0, but if I went through the path of A, it only takes, say, 6 minutes, right? 6 minutes, and then C can now start. But see, after 6 minutes, B is still not complete. B needs 9 in order to complete its task, right? But then remember, C depends on the fact that A and B have to be done. So that means even though you finish off A early, you still have to wait an extra 3 minutes for B to complete, and that way C can then start. So that means when you're doing this, you're looking for the longest time, as opposed to Dijkstra's algorithm, you're looking for the shortest path, right? In this case, I can see that the minimum amount of time, or what's the amount of time required in order for C to start, clearly, C cannot start until at least 9 minutes, and assuming that B finishes exactly at 9, but that's the minimum time requirement. That's the earliest start time that C can do in order to start. They have to wait till B is done. So this is considered a critical path, but let's just continue on with these boxes so that you can understand what I'm doing. I'm just going to do these early times and early start times and late start times, later start times. So here we go. I like to think of it as this is the A component, and then this is the B component. Okay, so when you're starting off at the very starting point, they're all both 0. And then if you take the path of B, this brings you to 0 plus 9. The earliest start time or finish time for B to complete is 9, right? Whilst if you go up this way, technically this is meant to be 6, but out of 9 and 6, which one should we account for? We realized that it had to be 9 in order for C to start, right? Then we do the same thing at what is the earliest start time for E? Well, E clearly comes off the D. D has to complete. So starting from point C, at this point, I can go down D or start of D, starting at 9 minutes. It takes 7 minutes to complete. So I know this is going to take me 16 minutes for D to complete in total once the timer has started. And then that means looking at this next point here, notice that if I went down the route of C, 9 plus 8 gives me now 17. But if you went down the route of D and then E, right, how long does that take? And we can see that it adds an extra 17, 9 plus an extra 17. And we can see that 9 plus an extra 17 gives me 26. Can you see what I'm saying there? So either you go down this route. So starting off C, if you went down that route, it takes 17 minutes. But remember, F can't start immediately because F relies on the fact that C and E complete together. So even though C finishes after 17, I still got to wait an extra, so 17 minutes means that I am still waiting for an extra 6 plus 3, 9 minutes. I'm still waiting an extra 9 minutes until D and E are complete. That way, F can finally start. So the earliest start time for F has to then be 26 minutes because that's the longest time that's taken, but it's also the fastest time that's taken for D and E to complete, and therefore C is also complete as well. Okay, so 26 is the earliest start time for F, and clearly the earliest finish time for F would then be 26 plus 12 is 38. So what we see here, okay, is that there's a pathway involved in order to get the earliest start time, right? When you're going backwards, it's what we call the latest start time. We're working backwards now. Before we were looking for the largest value because we wanted to know what's the maximum amount of time or minimum amount of time for those activities to finally start. We had to look for the bigger numbers. But when you're working backwards, you see, you're now looking for the latest starting time. And just to illustrate my point again, here, if I ask you what is the latest starting time for C, knowing that you can do A in 6 minutes, right? And you can do this in 9 minutes. Now, A activity doesn't have to start exactly when it starts at 0. How many minutes can it start until for them in order to finish exactly at 9, right? Or to start at 9? Well, you see, because it only takes 6 minutes, there's a float or at least a space of 3 minutes available. There's 3 minutes available in order for A to start. So A can start, say, 2 minutes in. 2 plus the 6 only gives me 8. They still finish before B even completes. See what I mean? So because of that, what we want to do is in order to find out how did I know that I can start at 2, I can start at 1, and I can start at 3 and still be fine because 3 plus 6 gives you 9, 2 plus 6 gives you 8, and 1 plus 6 is still 7. It still fits. You can still complete A within a time frame of 0 to 3 seconds. Does that make sense? So when you're working backwards, what's interesting is you're not looking for the longest time in order for it to finish. You're looking for the minimum. You're looking for the smallest time that is needed. So here, we can work backwards from here. 38 is the minimum time required. So if you go backwards, that means take away 12. 38 take away 12 is also 26. So that means the latest start time and the earliest start time for activity F to begin is exactly 26. There is no giveaway. In order to finish at 38, this had to be 26. So that's the latest start time that you can do, right? So earliest is 26, latest is 26. Really, technically, this is a float of 0. There is no giveaway. F has to start 26 minutes afterwards. There is no other reason for this. So this is called a critical path. So F is a critical activity, okay, that it has to be done because the start time and the finish time is exactly the same. There is no giveaway between them. Then from here, notice that 26, right? If I went down backwards, well then what's the latest start time for E? In order to make sure that I land at 26, well, it would have to be 16. That's the latest start time. If it starts at 16 and add an extra 10, well, of course you would get 26. So down here is 16. But then if that's true, you see, you can also work the other way around as well. You can say, well, 26, if I worked backwards, what's the latest start time for C? What's the latest start? 26 take away 8 gives me 18. True? Is it 18? Wait, 26. Yep, 18. But see, the problem is if I said the latest start time for C is 18, if I wrote 18 here, you can see a problem here. See, 18, if I went down this pathway, so 18, if I added the 7, that gives you 25. 25 plus 10 now gives me 35. So that means E would be delayed. So 18 can't be the latest start time because it may work for C, it won't work for D and E. So the latest start time, you have to account for the smallest value you can get. So it can't be 18. 18 was because I did 26 take away 8. Then what about here then? Well, 16 from here to get back to that same point to start of C. Well, 16 minus 7 gives me 9. So out of the two, you see, out of the two, the latest start time has to be 9. Has to be 9 for C. Because if C starts at 9, then 9 going down to D. Okay, so start time for C is 9. Then 9 plus 7 gives you now 16. 16 plus 10, I will still make it on time. You see what I mean? Whilst the other one, if I went with 18 before, that won't work. So even though I can still finish on time for C, it doesn't account for D and E. And because of that, the shortest time, you're looking for the smallest value. See, this is where it gets confusing. So LST, you're looking for the smallest, whilst EST, you're looking for the largest. And that's what generally gets students confused, okay, as you're going through it. And it can be confusing. You just got to do a couple of practices to get used to this idea. But here we go. So we got from 9, and then we're going to go backwards again, same thing. So if I went down this way, 9 minus 6 tells me the latest start time has to be 3. So that makes sense because, like we said before, they don't have to start. Activity A doesn't have to start at 0. It can start at 3 and you still finish at 9. It is okay. But then out of these two, let's have a look. If I went from 9 and it went down to B instead, 9 take away 0 gives me 9. That means B, the earliest start time for B is 0, but then what's the, it takes 9 duration to finish. So this is the latest start time or finish time for B. B needs to finish at 9 in order to meet C's requirement, right? So I now know that this has to be 9 as my latest start time. And then going backwards again, so from 9 minus 9, that gives me now 0. So you can see that the latest start time for A can be 3, but the latest start time for B would have to be 0. So out of the two, you can't afford to tell them all to start at 3. You have to then know that it takes, if you're taking the route of B, you have to start immediately in order to finish here in 9 minutes. And that way C can then continue its pathway. So what I've done here is I've got an EST versus an LST. And what I've highlighted, as you can see there, is the critical pathway, because that can't afford any mishap. So activity B has to start on time. There's no giveaway, whilst A can have an extra 3 minutes giveaway, right? Once B finishes, C immediately can start. If they wanted to, they can start at 9, or they can, C should start at 9 anyway. But anyways, at that point, you see, if they don't start immediately, so if D doesn't start, that's a problem because D relies on the fact that B is complete. A can easily complete in between there. But what you'll see here is D will finish off the activity starting from 9. 9 plus 7 gives you 16. And then E will follow from that. Once D is finished, E will follow an extra 10. And that will ensure I will meet the requirement to start at 26. Because 9 plus 7 plus 10 gives you 26. So what I'm highlighting there is what we call a critical path. Because you just can't afford to lose time. D has to start immediately as soon as B finishes, and E needs to start immediately as soon as D finishes to all meet the requirement of 26 minutes. Okay, and then same thing for F. In order to meet the requirement of 38, finishing off at 38, the only way is that F has to start immediately after E. So what I'm coloring there is what we call a critical path. Okay, but we can see that C, so I'm just going to go back here, C doesn't actually have to start at 9. C can actually take some time because C only takes 8 minutes. And from 9 to 26, it looks like they can start at 18. At 18 minutes into the whole process, 18 plus 8 will give you the 26 anyway. So C can start from 9 to 26. So 26 take away 9 is 18. But minusing the 8 as well, they have a 10 minutes buffer. Does that make sense? It takes, there's a duration, a float of 10 in order for it to play around before it needs to start. So you can see that if we work backwards here, they could have started off at 3 minutes in, and then they start, and they'll still finish at 9. Once they finish at 9, right? 9 plus 8 is 17. But from 17 to 26, you still have an extra 8 minutes left over. Is that right? Wait, let me just calculate my maths again. 17. Since 9 plus 8 is 17. 17 to 26 is 9 minutes. Sorry, 9 minutes. So that means there's a 9 minutes buffer. They can start 9 minutes afterwards, which means 9 plus 9 gives you 18. They can start off at 18. There's still 9 minutes that they can afford before C needs to start. Because C can still start at 18 minutes rather than this 9 here and still meet the 26 minutes, if that makes sense. Whilst B, activity B, as soon as it finishes, D has to start. Once D finishes, E has to start, and they'll meet exactly at 26. But the activities that didn't have to matter, A and C, those have a bit of giveaway. And that giveaway is what you're calculating and you're going to be learning, which is what we call the float times. Okay? So that's the gist of the idea. And that's where it does get tricky. You got to practice a couple of times to get your head around this. But that's how I've done it. So I've drawn the activity network. I've done the EST, LST. And now they're asking in part B, complete the critical path analysis, which I've highlighted. And then part C, they ask you to write down the critical path. So B is critical, D is critical. So as soon as B finishes, D has to pick it up. And then once D finishes, E has to pick up the work. And then once E finishes, F has to pick up the work in order to complete it all within 38 minutes. So D, when they ask you, what is the minimum time required to complete the project? Well, we know the minimum time required is 38 minutes. They can take longer, but we're looking for the minimum time. Okay, so 38 minutes. Assuming that everyone does their job correctly, B finishes activity exactly 9 because it takes 9 minutes to complete it. And then D will follow straight away and can complete it in 7. E will complete theirs in 10, and then F will complete it in 12. The earliest time that they can finish in it all is 38 minutes. That's the fastest they can do. Whilst activity A and activity C, they can kind of start, they've got a bit of freedom to start whenever. And so that's what we're calculating here. We're calculating the differences, and we know that A can start 3 minutes after, and we know technically if you